So let's take a look at this problem, which involves the normal distribution and some properties of random variables. So make sure that you've tried the problem before you listen to the little explanation and look at the solution. Time yourself or work on it for about between 12 and 15 minutes. So we've got this team composed of 4 runners. Now the key here in this problem is that each of the runners' times, assume that the individual times of the 4 runners are all independent of each other. That's key. And that the individual times are approximately normally distributed for each runner. So that means we have 4 different distributions here, because we've got, runner 1 and all of his times create one distribution that is approximately normal with a mean of 4.9 minutes and a standard deviation of 0.15 minutes, etc. for runner 2, runner 3, and runner 4. And then the question is going to ask us if we combine those 4 distributions to create one distribution that represents the team's time. And we can do that conveniently since all of the times are independent. So question this part A here. Runner 3 thinks he can run a mile in less than 4.2 minutes. Is that likely to happen? That's just going to be a basic calculation using properties of the normal distribution. Part B is asking us to consider the distribution of possible team times. Now that's going to be approximately normal because to create the team time, we're just going to add the 4 runners' times. And since each of the runners' distributions are approximately normal, then the distribution of team times will be approximately normal, since we're just adding those random variables together that are independent and normal. So the mean and the standard deviation, we can find those conveniently using the rules of random variables. And then part C asks us, what's the probability that the team will beat its best time? So in order to compute that, that's going to be another normal distribution question, but we're going to have to use the answer from part B to figure out part C. So let's take a look at my solution. So notice here, I start off for part A by defining the variable. So I'm defining what I'm calling x here, and that's just going to be time for runner 3's mile in a race in minutes, one single time. X is approximately normal with a mean 4.5 minutes and a standard deviation of 0.14 minutes. That was given in the problem, but I'm writing that down. I'm showing that I understand appropriate notation, and I understand that that's the key piece of information for the problem. So then I found the z-score for that time of 4.2 minutes. Notice I'm showing the formula for the z-score, substituting in values. I'm showing that calculation. And then I'm figuring out what part A is asking. I'm using proper probability notation. I'm looking for what is the chance that the runner beats 4.2 minutes. That means that's the chance that an x value for his next race is less than 4.2 minutes. I'm using proper probability notation in terms of z-scores. And notice how I compute that probability. Now on my calculator, I probably did normal CDF, negative infinity, comma, negative 2.1429. But notice I don't write the calculator speak in my answer. Notice I've got my picture here showing kind of my understanding that the distribution is normal, and pictorially I'm shading in the area that corresponds to the proportion, the probability that I'm solving for. And then I write a sentence to recap that. Runner 3 has about a 1.6% chance to run a mile in under 4.2 minutes. In other words, it's not likely that he'll beat his time. So notice I've defined my variable. I've written down key given pieces of information about the distribution. I'm computing the test statistic, the z-score in this case, showing my work, using proper probability notation, drawing a picture, writing a sentence. All in all, the math's not that bad, but you want to clearly communicate your answer. That's the key here. Now in part B, I'm finding the mean team time. So notice I define this mu sub t to be the mean team time, that's the parameter there in minutes, and sigma sub t to be the team standard deviation in minutes. Now, since I'm just adding some independent random variables together, like I'm adding all of the possible times for runner 1, runner 2, runner 3, and runner 4, looking at all possible combinations of those times added together to create the team distribution. So to find the mean for the team time, that's really easy. I'm just going to add the mean, the parameter mean, population mean, for each of the runners together, and that's it. And I'm allowed to do that because the times for each runner are independent. So using this rule, sort of that the mean of the team is equal to the sum of the means of the runners, that's only, I'm sorry, that's going to work regardless if the runner times are independent. But the rule for the standard deviation, the runner times need to be independent. So I could always compute the mean team time. I'm sorry, I misspoke there. That's going to be 18.9 minutes regardless if the runner's times are independent or not. But the team standard deviation, in order for this calculation to work out nicely, the individual runner times need to be independent of each other. So I remember that I could add the variances together of each of the distributions and then just square root. The variances add, the standard deviations don't. So I just had to remember kind of the quote-unquote Pythagorean theorem of statistics there. So that takes B. Now I'm going to use that information in part B to answer part C, because part C is asking what is the chance that the team runs the race that in less than 18.4 minutes, which is its best time. So I've drawn the picture corresponding to what that question's asking me. I got the picture right here. I went ahead and said that T was the team time in minutes. I probably should have thrown that variable definition up there in part B. I mean, I defined what mu sub T was, but maybe I could have done that in part B too. I found the z-score corresponding to that 18.4 minutes for the team time. Notice I'm not saying x minus mu over sigma. I'm saying t minus mu over sigma. So I'm properly using the random variable that I have defined. I'm using computing the z-score for this team time, so it's t, the statistic, minus the parameter, which is mu sub t, the mean, divided by the standard deviation, sigma sub t, for the team. So I found that z-score. And again, I'm using proper probability notation in terms of the random variable that I've defined, proper probability notation in terms of the z-score, and I found that probability. Again, I did not need to say normal CDF negative 99999, comma, negative 1.665. Didn't need to say that. Showing the computation for z, that I know the z-score formula, how to find that test statistic, the picture, the definition of the random variables, proper probability notation, all these things constitute quote-unquote work. I'm demonstrating my understanding of the problem clearly, efficiently, succinctly. Don't need the calculator speak. And then I'm just going to recap everything I've done with a sentence. There's about a 4.8% chance that the team will beat its time in the next race. And I'm done with that problem.